Hello, my name is Radek, and in this workshop, I will introduce our plugin for imaging fluorescence correlation spectroscopy for FIJI, and I will also introduce imaging fluorescence correlation spectroscopy as such. I work at Nanyang Technological University in Singapore. Jagadish works at Genome Institute of Singapore. But we all got involved in this topic while working with Thorsten Wohland at National University of Singapore. Before I get to the plugin itself and showing you how to use it, I will introduce Imaging FCS as such. So we are starting with noisy images. This is a turf image, cell, cell membrane, and you can see the image is quite noisy, but we are not now interested in the noise, like the static noise from pixel to pixel, but if we, let's say, look at, take a time series of such images and look at each pixel, you will also see noise and intensity fluctuations in each pixel over time. And these are caused by several processes. One of them is the instrument noise. In this case, would be mainly the camera readout noise, which is not interesting for us because that doesn't tell us anything about the sample. We are more interested about the other sources of noise. Namely blinking of fluorophores, so they can be transiting between dark and bright state, and also the motion of fluorophores. If we have fluorescent molecules, or can say in general fluorescent particles, because those could be complexes of molecules which move. So they will be at different points in time contributing to the signal in different pixels. So if we are looking at this intensity in a single pixel, it will be changing depending on how many fluorophores are at that moment in the pixel, and that will be changing as the molecules move around or as they blink between bright and dark states. The blinking of most fluorophores happens on a time scale which is faster than what is accessible by imaging FCS, because they are limited by the camera frame time, which practically we use frame times typically on the order of milliseconds. But of course, there could be cases when even some blinking could contribute to what we see. But in most cases, the fluctuations we see and we are interested in are caused by movement of fluorophores or the fluorescent molecules or the fluorescent particles. So now, if we look at the signal coming from a single pixel, that means it will be fluorescence intensity coming from a small volume in the sample. I will later get to how that is defined. So just briefly, in this case, in the lateral dimension, it will be defined by the project camera pixel convolved with microscope point spread function, and because this is a turf image, so in the axial direction it would be defined by the penetration depth of the evanescent field. Then if we look at the fluorescence intensity time trace over time coming from such a voxel, then if a fluorescent particle is moving through the voxel, it will result in a burst of fluorescence intensity. And if we measure the duration of this burst, we know how long the fluorescent particles needed to transit through the voxel. And if we know the size of the voxel, then we can derive information on mobility of the particles, their diffusion coefficient. So that's something which is obviously interesting. So how do we measure the duration of this burst? So in fluorescence correlation spectroscopy, we do it obviously by correlations. But let's get to what is required to perform this type of analysis. So we need a small observation volume and not too high concentration of the fluorescent particles in order to see pronounced fluctuations. If the volume is large and there's a large number of fluorescent particles present on average in the volume, then the fluctuations will be effectively averaged out and it will be difficult to perform the analysis. And we also need single molecule sensitivity because these bursts are coming from single particles, which may be a single molecule. So in that case, we need to be able to detect such fluorescent changes in fluorescence intensity. So now, how do we do the correlation analysis and how do we obtain the duration of these bursts from the correlations? So let's take the time trace and multiply it with a replica of it, which is shifted in time. As is shown here. So we are shifting the replica in time, and we are introducing different lag times tau. And of course, if the shift is small, then all the bursts will still overlap to some extent, and this product is high. But then when the shift is longer, the overlap between the bursts is decreasing, and at very long shifts, which are longer than the typical duration of the bursts, there is no more correlation between the bursts in the original time trace and its replica, and the product converges to the asymptotic value, which would be the square of the average fluorescence intensity of the time trace. Then we typically normalize the correlation function by this square of the average fluorescence intensity. And you might find two different definitions of correlation function used in FCS. One is just like this, and the other is that we subtract the asymptotic value. So then we make the correlation function converge to 0. But both definitions are equivalent. The difference is only in the offset. One more thing which is needed is sufficient temporal resolution. So in order to get the typical duration of these bursts, we need to measure with higher temporal resolution, at least an order of magnitude better than the typical duration of the burst, and than the typical time scale we are interested in. So this is just to show schematically that when we have a bigger particle which is slower, then the width of the correlation function is larger. And when we have, on average, more fluorescent particles in the observation volume, then the average signal is proportional to the intensity of n particles, where n is the average number of the particles, and the bursts are proportional to the signal of an individual particles. And then the amplitude of the correlation function is inversely proportional to n, to the average number of particles. So we don't get only the mobility of the particles, the diffusion coefficient, but we can also get the number of particles, so their concentration. So this is how we can obtain the small volume. So one experimental implementation of imaging FCS is using a turf microscope, in which case, as I said, in the lateral direction, the observation volume is defined by the projected camera pixel convolved with microscope point spread function, and in the axial direction, it is defined by the penetration depth of the evanescent field. Another possible implementation is using light sheet microscope. In that case, the axial direction, the voxel will be defined by the thickness of the light sheet. I don't show it here because all the examples, which I will be later showing to you how to process them in the plugin, they all come from TURF. Of course, imaging FCS can be applied also on light sheet images or principal images acquired with other microscopy modalities. So then, getting back to the how the voxel is defined in the lateral direction. So we have camera pixel, which, and the effective area is then the projected camera pixel convolved with microscope point spread function. So it is schematically shown here, because if the point spread function is larger than the projected pixel area, then of course, if we are looking, let's say, at the signal in this pixel, then a particle, which is actually in an area corresponding to a different pixel, will also contribute to that signal. So that makes the effective area larger. So as shown here, if the pixels are large compared to the point spread function, then of course the pixel is the main determinant of the area, while in case the pixels are small compared to the point spread function, then the point spread function is the main influence of this. So we have the small observation volume, and then we also require single molecule sensitivity and sufficient temporal resolution, which typically, for example, for diffusion of molecules in a membrane, we need on the order of milliseconds. We typically use electron multiplying CCD cameras, but modern scientific CMOS cameras can also be used for imaging FCS, and we have also used them. So they provide sufficient sensitivity, and of course, they can provide a sufficient temporal resolution, although sometimes we cannot take the full frame of the camera, but we need to take only a smaller region of interest to achieve sufficiently short frame time. And we can now proceed to the actual plugin. So you can, if you don't have the plugin yet, you can download it if you add Imaging FCS update site in FIJI, or you can also download the plugin from the website of Thorsten's lab. I'll show you here. So this is website of Thorsten's lab, and here under resources, there's Imaging FCS for ImageA. There are also interactive FCS tutorials. So if you are interested in FCS and want to learn the technique, so this is a good starting point. So currently, this is still refers to Imaging FCS version 1.52. The latest release is version 1.6. So if you update via the update site in FIJI, you will have version 1.6. This will of course get updated soon. So here you would get the slightly older version. You also can find out what are the other requirements you needed to run the plugin. For example, you need Apache POI for saving the analysis results, so that you can load them back if you want to continue in the analysis where you stopped. And you can also find an example of a turf image taken in a lipid bilayer, so you can use that just to have some data if you want to play with the plugin. And of course, you can find here also publications related to Imaging FCS. So if you are interested in the technique, you can find all sorts of information here. And now that I've done with this introduction, let's go to FIJI and start the plugin. So here under plugins, we go to Imaging FCS. As I said, the current version is 1.60. Now, when it loads the plugin, you could see that it was looking for graphics card, compatible graphics card for GPU acceleration, which I don't have here, so I cannot use the GPU acceleration. But if you install it at a workstation with a suitable graphics card, then you can benefit from GPU acceleration, which is useful if you want to process especially larger images. Another message which we got here is that it cannot read Imaging FCS config file. The reason is that we haven't yet created this file, and we can create it here under experimental settings. So these are all the parameters which refer to your microscope setup, such as magnification, numerical aperture of your objective, or the pixel size of your camera, wavelengths, fluorescence emission wavelengths which you are using, and also the point spread function size. I will get back to this point spread function size because this is an important parameter, and I will explain you how it is how we can calibrate it. Yeah, so this is the lateral point spread function, which is all we need in case we are looking at diffusion in 2 dimensions. So this is the case, for example, in diffusion of a molecule in a membrane, because the molecule is restricted to one surface. If we are looking at, using light sheet microscope, and we are looking at molecules which diffuse in all 3 dimensions, then we also need the axial point spread function, which would be determined by the thickness of the light sheet. But in this case, there's just a large number because we don't need this parameter, so we don't need to touch it as long as we are looking only at 2-dimensional diffusion in membranes, which is what I will be showing you now. So this is, of course, something which typically you will be using similar parameters all the time, because you probably use the same objective lens, you have the same camera. So in this sense, if you have to fill it in every time, it's a bit of a nuisance. So we can fill it in once, and then we press here write configuration, and this will write configuration file, which will store these values. And next time when you start the plugin, it will load these values automatically. So let's do here some small change. I change, for example, the wavelengths, because actually the pixel size and the magnification, they are what will apply to the data that I will show you. Now we write configuration, and we can exit plugin. Let's start it again. And we didn't get the message about the configuration file. And let's see the experimental settings. You see there's the wavelengths which I filled in. And let's now load some data. We start with a simple sample, which is just supported lipid bilayer. So I open the image, and I will now press button use. Will then use the active image in the plugin. Now, if I click on a pixel, it will calculate the correlation function. I can see here the density time trace. If I click on different pixels, I'm getting the correlation functions in those pixels. So this is just the correlation function. In order to get the diffusion coefficients and particles numbers, I need to fit the correlation function with a theoretical model. So I have to select the model here. There are 3 options for TERF. 2-dimensional diffusion, this is the model I want to use in this case. There is also the model for three-dimensional diffusion, that would be for light sheet data, and there is a model for two-color cross-correlation that I will show you later. So now we stay with this model, and here fitting is currently off. So if I switch fitting on, we'll open window with these are the initial fit parameters. So if I now click on a pixel, it will calculate the correlation and also do the fit. To have the fit correct, I of course need to have all the parameters correct. Another important parameter besides what we set here in the experimental settings is the frame time, which of course defines the time axis. And in this case, it is 1 millisecond, which is correct for this data. What else we have here is the first frame and last frame. So this time series consists of 20,000 frames. So we typically we need something on the order of tens of thousands of frames for imaging FCS. To again depends on what are the typical timescales you are looking at. You need to have to get good statistics of the correlation for the longest lag times you want to see in the correlation. You need to have experiment which is much longer than the longest lag time you want to go. So we typically work with frame times on the order of milliseconds, and we are taking tens of thousands of frames, 50,000 frames, typically up to 100,000 frames. This number here, this is the background value which is subtracted for the correlations. It will automatically take the lowest pixel value in the time series. You can of course put there a manual value. This does not affect the values of the diffusion coefficient you get. It will only influence the amplitudes, that means the concentrations, the particle numbers. And of course, I forgot to mention here, you have the first frame and last frame, but you can also, if you change here the number, you don't have to start from the first frame. You can start from any frame. So for example, if there is anything weird in the intensity time trace, for example, in the beginning of the intensity time trace, you can cut off the part by starting at a later. And of course, I just did the correlations for individual pixels. I can also do it for all pixels by pressing all here, or I can do it for a certain region of interest. So I can draw a region of interest using here the tools I have in FIJI for defining regions of interest. I can do rectangular region of interest, and if I press ROI, it will correlate the correlations for the pixels in the region of interest, and here it will update the parameters map, so it shows the different parameters of the fit model. N is the particle number, D is the diffusion coefficient. You can see the distribution of the diffusion coefficient, and that's basically those are the parameters of interest in the case of this simple model. There are other parameters. I can have, for example, two different diffusion coefficients. If I have particles, faster particles, slower particles, and their fractions, so I can have much more complex models. So then I will have more parameters mapped corresponding to these models. If I click on a pixel in the parameter map, then I will see here the correlation function and fit for that particular pixel. Of course, these parameters will be correct only if I have all the settings correct, and I need also to have, assume I know my camera, pixel size, numerical aperture, magnification of my objective, but I also need to know the point spread function. And so let me now get to this point spread function and how it is defined here. Let's get back to these slides. So the point spread function we need for the model is the 1 over e square radius of the point spread function, and we can say that this value is proportional to the wavelengths and inversely proportional to numerical aperture. So the parameter we are filling in the plugin is this sigma 0. So it is the value which is independent of numerical aperture and wavelengths. And how we can of course image, for example, a small bead, and then from the image fit the point spread function. That's one way how we can get it, but we can also do it by calibration in a sample which exhibits free Brownian diffusion. This is of course important, as I will later discuss. If this is not the case, if the diffusion is somehow abstracted, if there's, for example, some transient binding, then of course this will not work. But if the diffusion is free, then, and if the diffusion coefficient is independent of the area we are looking at. So if we can change the area, and in each case we know exactly what the effective area is, then the diffusion coefficient we get should still be the same. And that's the idea behind the calibration. Because since we have an image with many pixels, so we can do the correlations for each individual pixel. So that's one area. Then we can get a larger area by pooling some pixels together. So we can, for example, do 2 times 2 binning. So we will have larger effective area, and we do the correlation and the fitting for such larger areas. And if we know everything correctly, we have the correct point spread function, then we should still get the same diffusion coefficient. Same goes if we do 3 times 3 binning. And here you can see in this plot, so this is the area on the x-axis, and y-axis is the diffusion coefficient. And different curves correspond to different value of sigma 0. So in case we have the correct sigma 0, then the diffusion coefficient is independent of the area. While if we have a wrong value, then the diffusion coefficient will be changing with area. Why? Because for different numbers of pixels, the point spread function contributes with different weight to the area. If we take individual pixels, the contribution of the point spread function is the largest. While if this is 1 pixel, this is 2 times 2, 3 times 3, 4 times 4, up to 5 times 5 pixels winning. And in this case, because the area defined by the pixels is so large, then the broadening by the point spread function is negligible. So then you can see that for these large binnings of pixels, the point spread function plays a minor role. So then it will for all values of point spread function, it will converge to the correct diffusion coefficient. Of course, there could be problems if, for example, you have bleaching. So then, as you are increasing the area, then there will be higher chance that the particle doesn't exit the area by diffusion, but it disappears somewhere halfway through because it was bleached. So in that case, you will see that even for the correct value of point spread function of the sigma 0, the diffusion coefficient will not be constant with area, but it will start increasing for larger areas because you have more particles which disappeared through bleaching in a shorter time. So the fluorescent burst caused by this particle was cut short by the bleaching event, and that means that it seems as if it diffused through the volume, through the area in a shorter time, and that will bias the diffusion coefficient. And this bias will be getting bigger for this increasing area. So that's how the idea of how the point spread function calibration is done. So let's go back to the plugin and do it. So we have here a tool for point spread function calibration. So and here, so we can define what is the starting value of sigma 0 we want to probe, what is the end value, and what is the step. And we start with individual pixels, so 1 times 1 binning, and we will go until 5 times 5 binning. So I will press OK. And of course, this will take a while. So you can see here the progress, but I will spare you the waiting. And I jump forward in time to the moment when this PSF calibration has finished, and you see the output here. So you see this is binning, and this is diffusion coefficient, and these curves correspond to different values of sigma 0. So we see that for the value 0.8, we get diffusion coefficient which is independent of binning, area. So that is the value which works here. Let's check, and that's the value we had there. So the correct value. Now, of course, it could be different for different setup. Okay, so this was a pretty boring sample. Lipid bilayer is great for doing the point spread function calibration, but let's now move to something more interesting. And I have another sample, which is also a lipid bilayer, but it is a phase-separated lipid bilayer. So it's a mixture of two lipids, which are, one is at fluid phase, one is at gel phase at room temperature. So you can see as also from intensity, you can already see that there are areas which are different. And of course, we expect that the different phase will be represented also in different diffusion coefficients. So in the ordered and disordered phase, we should see differences in diffusion. So let's try. So we click here. And you see that the correlation function doesn't look as nice because the diffusion is very slow. So we don't really see nicely the convergence of the correlation function compared to when I click here to the darker area. So this is obviously the liquid disordered phase, where I can see nicely the nice correlation function in the brighter area. And you can see that there are also the intensity time trace looks a bit funny. So maybe it will help if we do some detrending of this time trace, which can be done here through bleach correction. So currently we don't do any correction. So we have here a few options. We can do exponential bleaching correction, which of course is the ideal model if it's bleaching, if it's purely bleaching, which follows nicely exponential kinetics. But as you can see, sometimes in the real samples, it's not the case. So we are usually using polynomial bleach correction, which is in a way more flexible. And we can select polynomial of order 4. That usually works quite well for most cases. So let's see. Now we are one because we changed the parameters. So this will reset the parameter map. And you see this this helped with the slow trends in the intensity time trace. So let's now correlate the whole image. And we are done. So this is the parameters map. So we can see clearly that also the distribution of the parameters corresponds to the different domains. So this is particle number, and This is diffusion coefficient. So you can see there's a bimodal distribution of the diffusion coefficients, which is not surprising. And if I select here a region of interest in the ordered phase, I see such correlation function. If I select it in the disordered phase, the correlation functions different. And you can also notice that the particle number and the diffusion coefficient seem to be somewhat anti-correlated. So I can have a look at a scatter plot of particle number versus diffusion coefficient, and you can see that how it looks. It looks like if you are familiar with 2D histograms in colocalization analysis, so this is what you would see for in case of non-colocalized channels. So yeah, this is what we somehow expected. And at this point, I will show you some more features of the plugin. So there is a function to save your analysis progress. So if we press here, then we can save it. And then again, we can read the saved file, and we can continue with the analysis where we stopped when we saved the file. Another useful feature is results table. So this generates a table which summarizes all the results. So that's another way how you can save the results, and you see that it contains all the settings for your reference, and then there are autocorrelation function, fits, and the fit parameters. So it saves all the results of the analysis. Okay, so now let's leave lipid bilayers and let's move to live cells. So the live cell image I have now loaded doesn't look very exciting. It looks pretty featureless, as the homogeneous lipid bilayer. It doesn't have the large domains like the phase-separated bilayer, but it doesn't mean that it's as homogeneous as the first lipid bilayer we looked at, because cell membranes are known to contain various domains, but the size of those domains are much smaller than those in the phase-separated bilayer, and that means they are not resolved in this image, but they still do affect the diffusion. And there are ways how FCS can sense how the diffusion is affected by, for example, these domains. And so I will, before we look at these data, I will briefly explain the idea behind it. A principle called FCS Diffusion Law. So we are looking at the residence time versus the observation area. So if in case of free diffusion, this is the residence time is proportional to the observation area. So this is in a way another way of saying that the diffusion coefficient is independent of the area, which is what we used when we did the PSF calibration. Now let's consider we have some obstacles to the diffusion, either some domains which transiently bind the diffusing particle, or there is a meshwork of obstacles which the particles can cross, but let's say they need some activation energy to cross these barriers. So they are sort of semi-permeable barriers. So when we are, for example, looking here at areas which are within one of these corals defined by the barriers, so the diffusion will be free. While we are looking here at a small area which is mainly dominated by the domain which transiently binds the particle, so then we have here a large offset because there is some time which the particle spends bound to the domain, so it doesn't leave the observation area. Then if we go to larger areas, then in the case of the meshwork, the effective diffusion coefficient will be slower because the particle, in order to cross such a larger area, needs to cross several of these barriers. While here again it will be, you will see some diffusion of dependence of the residence time on the observation area, which again, from if we look only at the larger areas, which are much larger than either the domains or these corals in the meshwork, which is what is accessible by typically by imaging FCS, we will just see a linear dependence of the residence time on the observation area. So we cannot, so it's still, in all cases, we see a linear dependence. But if we look at the offset, then we see a difference. So if it is close to 0, that means we have free or nearly free diffusion, while positive offset means there is some transient binding, some small domains, while a negative offset means that the particle needs to cross some semi-permeable barriers. And of course, to get this offset, we need to get some look at the dependence of the residence time on the observation area. So we need to do measurements at different observation areas, but that's in a way straightforward in imaging FCS because that's the same what we did when we did the PSF calibration, that we do binning of pixels to generate different effective observation areas. So this is just an example that if there's just a supported lipid bilayer, then the intercept is 0. As expected, the diffusion is free, no obstacles. While when there is this is the phase-separated bilayer, which has a large positive offset, and this is to simulate the semi-permeable barrier. So this is a lipid bilayer prepared on a patterned substrate, and so this is patterned in such a way that the spacing of these barriers is large enough to be resolved in the image, and so we can see here the transition of the two regimes, the free diffusion within one of the corals, and then the slower diffusion when the particle needs to cross the barriers. This results in the negative offset. So now let's get back to the data. and let's perform diffusion law analysis. And so we start with 1 times 1 binning up to 5 times 5, and let's calculate the diffusion law. Here it is. So now we can fit the diffusion law, and we see there's a positive intercept. That doesn't come as a surprise because we were looking here at diffusion of a GPI anchored protein, and those are known to be associated with cholesterol rich domains. So in a way, we expected that it will have this transient binding. So let's now keep this plot. For reference, and let's look at the same cell after treatment with M-beta cyclodextrin, which is known to remove cholesterol from membrane. So I have loaded the data for the M-beta cyclodextrin treated cell, and I will do again diffusion law calculation. And here it is. So I will fit it. And now you see that the intercept is still a positive intercept, but it is reduced to 0.12 compared to 0.25 before the treatment. And of course, if you now got interested in Imaging FCS and the Imaging FCS plugin, and you want to explore it a bit more, you might not have suitable data to analyze it. So in that case, you can generate some data to play with by simulating them. And we have here a tool to simulate data. Of course, this is not just the purpose of it is not mainly to play with the plugin if you don't have real data. The main purpose is that this is useful when you want to analyze the performance of Imaging FCS. For example, how does the temporal resolution and the number of frames affect the results and the accuracy of the analysis for different diffusion coefficients and such things. Also, it was useful to test the bleach correction and whether the bleach correction in any way affects the results of the analysis. I will show you here. We can open the simulation panel and set up the parameters for the simulation. So let's, for example, increase the camera noise to make it a bit more noisy, increase the number of particles but make them less bright, and maybe we make the diffusion 0.5, and let's introduce also some bleaching to simulate the situation where we have bleaching. So I'll put some non-zero bleach time, and now I can start the simulation, and then we can analyze the results and see whether we got the correct diffusion coefficient. So here are our simulated data. Let's first see the bleaching. So I switch off bleach correction, and I try to correlate a pixel, and you see there's considerable leaching, which is what we wanted. So now let's switch on leaching correction. Look at the same pixel. You see it got clearly much better. So let's now correlate all pixels and look whether we get the correct diffusion coefficient. So remember, in the simulation we set the diffusion coefficient to be 0.5 micrometers square per second. See progress. And it's done. So here are the correlation function, and these are the parameter maps. So we see diffusion coefficient, and it's just the different units, but it is 0.55 micrometer square per second. So we have a good agreement with what we simulated. So I think this is quite enough for imaging FCS, but we can also do, if you remember, we have here this dual color FCCS model, so we can do imaging FCCS. So before we do it here in the plugin, so let me again briefly mention the principle behind FCCS. So we are now looking at time traces in two different channels. So we have particles labeled by different fluorophores, and if they move independently, then the intensity bursts in the two channels are not correlated. And if we do a correlation, not an autocorrelation function, but a cross-correlation function, and we cross-correlate these two time traces, the cross-correlation is flat. On the other hand, if the two particles, let's say if it's one particle labeled by two different fluorophores, then the bursts appear at the same time, and there is high cross-correlation between such time traces. And of course, the amplitude of the cross-correlation function relative to the amplitudes of autocorrelation functions, that tells us how strongly correlated are the traces. What is can tell us what is the fraction of the particles which are double labeled, which contribute to those channels. So this is an example how illustration of imaging FCCS. This is an image of cell membrane in two channels. So it's taken with a single camera using an image splitter. So this is just the overall image. Then the FCS recording was done in a smaller region of interest in order to get sufficient speed, sufficient time resolution. And then for each pair of corresponding pixels, we get autocorrelation functions and a cross-correlation function. And then if we fit them, we get parameter maps. So we have diffusion coefficients for both autocorrelation functions and for the cross-correlation function, and also the particle numbers. And then from the particle numbers, we can calculate the map of cross-correlation amount Q. So the cross-correlation amount Q, that's defined as the ratio of the amplitudes of the autocorrelation to the cross-correlation, but we always have to take the autocorrelation function with the lower amplitude, because basically the limiting factor, because one of the particles, let's say, can be in excess. So then the one particle which is less abundant will be the limiting factor, which limits how many particles can be there which are double labeled. So let's say if we have two proteins, one is red labeled, one is green labeled, and we want to see how strongly they interact. So then, of course, if one of the proteins is in excess, so it will be the less abundant version, which is the one that limits how many complexes of the two proteins. So that's the idea how cross-correlation amount is defined. Of course, it is just a, say, semi-quantitative measure of the interaction, because we are neglecting here a lot of factors which are important if we wanted to do a rigorous analysis of FCCS, such as brightnesses of the part of the two fluorophores in the two channels, spectral crosstalk, and so on. But in the first approximation, it is a useful measure how strongly the particles in the two channels interact. Now let's go back to the plugin and let's load some data which were recorded using the image splitter, so where we can perform the FCCS analysis. So I have loaded an image of a cell. In this case, it's not yet real two-color FCCS, because this was done using a 50-50 splitter in the image splitter. So basically these two channels are the same signal. So we expect we should see very high cross correlation. So let's do first some necessary adjustment in the experiment setting. So since there's GFP, so let's say it's 515, and because it's the same color in both, so let's put lambda to also 515. It doesn't matter so much unless we want to be quantitative in the diffusion coefficient. Then frame time in this case was 4 milliseconds, and because we want to do FCCS, so we need to input here cross correlation function distance. So they are shifted in y direction, so x shift 0 and y shift would be half of the image size, so it means 64 pixels. And as the model, we select dual color FCCS, and now I again can click on a pixel, and let's see the correlation function. So now we see just one function, which is the cross-correlation function. So if we want to see the autocorrelation functions as well, we have to switch on here FCCS display. So I again click. Now I see autocorrelation functions and the cross-correlation function. And of course, as expected in this case, the cross-correlation is very high. You can see that the correlation functions are rather noisy. So it might be, so maybe there's not enough signal in each pixel. So we can start with binned pixels. So we can do 2 × 2 binning. So we will take a larger area, and that will make the correlation functions smoother. See the correlation functions become smoother. And now we can again we could correlate the whole image, but in this case, because you see there are areas which are outside of the cell. So if I click on those pixels, there won't be any interesting correlation. So in this case, it would make sense. You see, this is the correlation functions from the pixel which is outside of the cell, and it's just noise. No useful noise. This is just useless noise. And so it would make sense, for example, to draw a region of interest, which is along the boundaries of the cell. Of course, you can use any tools which you have available in FIJI to define the region of interest. You could, for example, use some functions in FIJI or some macro to segment the region of interest, so that you only correlate what is the cell and what makes sense. Sometimes, of course, even some points in the cell, there will be no correlation because maybe the membrane is not flat, so there might be areas where the membrane is further from the glass surface, so it's outside of the evanescent field. So there might be, of course, some pixels which will not have any usable correlation. And you see what happened because I correlated here outside of the cell in a pixel where there was no correlation. Then it affected the parameters of the fit, and now you see the fit failed. The reason is that the fit, the results of the fit of the previous pixels are used as the starting values when fitting the next pixel, which works, of course, very well if the pixels are, if the fits, you can get the fit converges and and all the pixels are similar, but it might cause problem when we come across some pixel where there's no correlation. So in that case, let's here I again resume to the default starting values, and I do the correlation in some pixel which I can consider to be a typical pixel, and then I can here fix the starting parameters. So then all the fits will be starting from these values. So even if there is a pixel which is I clicked wrongly. So if there is a pixel which doesn't have any correlation and the fit values go wrong, so it will not affect fitting of the subsequent pixel. So let's now, just for fun, take a region of interest, which is partly in the cell and partly outside. So the fitting is done. And here we see the parameters map. And you can see that now if we are looking at the map of particle number for the cross correlation function, and you can see that some values here in the area which is outside of the cell. Well, the reason why we see these values is because here, where there is no cross correlation, not even any autocorrelation, then the amplitude is very low, so it's apparently high particle number. Of course, that in reality there are no fluorescent molecules. So we have here one functionality for thresholding the values, so that can help us to reject outliers. So here we can limit the thresholds on values which we accept and which we don't accept. So for example, here we have some apparently very high values of particle number. So let's put some limits on particle number. Let's try based on here. For the cross correlation, so let's try to use it. Filter. Now we see we are still have here these mostly these weird values. So let's try to cut down on it further. Okay, and now we finally start seeing those pixels which are inside of the cell. So that is this here, this distribution. So maybe we can even and of course we can then still hear some pixels which are obviously outside of the cell, so the correlation functions clearly don't make any sense. We could also apply some thresholds, diffusion coefficient, and also on the asymptotic value. So ideally, the ideal asymptotic value in our definition of the correlation function is 0. So we can limit what the asymptotic value should be. Again, there could be some fits which fail, especially where there is just some noise, and the asymptotic values could be all sorts of values, and we can also filter the threshold, the autocorrelation function. So for example, we can And in this way we can get the we can reject those values in those pixels which don't make sense, and we can get the meaningful values and the distributions of only those pixels where the fits and the correlation functions are certain quality. Another map of interest in the case of two-color fluorescence correlation spectroscopy is the map of the cross-correlation amount Q. So that's the last map this stack of parameter maps. So you see that, of course, in this case, the cross-correlation amount is high, which is what we expect. Here, before the cross-correlation amount map are the maps of valid pixels for the cross-correlation and the autocorrelations. And basically, if I here apply some thresholds, so I don't delete the values which are outside of the threshold. I just hide them by setting those pixels as invalid. And by resetting the thresholds, I can always get the values back. Okay, and now let's go to the real two-color FCCS data. So now I have loaded data from the actual two-color fluorescence cross-correlation spectroscopy. There is a protein, it's a positive control, so the protein is labeled both by EGFE and M-Apple. So we have to change here the second wavelength, so it's red protein, so something like 600 nanometer could be used. The rest of the settings should be still okay. We are using bleach correction polynomial, and we are doing 2x2 binning. So let's have a look. And you see there is some cross correlation. Of course, it is not as high as with the 50-50 splitter. So let's now define a region of interest. And try to read the cell somehow. It's not perfect, but let's now correlate the region of interest. And here we have the results, the cross-correlation functions, and here is the parameter map. I will make it a bit bigger. And let's look at what is interesting to us. That is the cross-correlation amount. So we go to the cross-correlation amount map, and we see that the cross-correlation amount is around slightly over 30%. It's, of course, it's much lower than with the 50-50 beam splitter, and it's not so surprising because when working with fluorescent proteins, especially the red fluorescent proteins, can have quite a long maturation times, and not all of them are also in bright state. So there is typically quite a high fraction of the fluorescent protein molecules which are actually not fluorescent. So some of the proteins, although they are labeled by both red and green fluorescent protein, then maybe only one of the fluorescent proteins is actually fluorescent. So that reduces the cross correlation amount. There are, of course, other features here in the plugin, such as, for example, number and brightness analysis, which is based on the works of Enrico Gratton. And I'm not going to go into all the functionalities. There's also one very useful function, which is live camera readout, which I cannot show you here live because I don't have a camera connected here. But it's very useful when performing experiments because you directly see, so the plugin takes out data directly from the camera and in real time calculates the correlation functions. So you don't need to wait until the acquisition has finished to correlate the data and see if everything is okay, but you can directly see it during the acquisition. So that's useful when you are optimizing, let's say, your experimental conditions. I can show that to you in a video. So know that this is a slightly older version of the plugin, so the layout of the main panel is a bit different than with the latest version. But now let's see, so started the live acquisition. So you see that there is some bleaching, so we apply or some trends in the time trace. So we applied polynomial bleaching correction, and you see we are starting with 2x2 binning, but now since we collected more data, we can reduce it to 1x1 binning, and we already have nice correlation functions, and we can look at correlation functions at individual pixels or at a selected region of interest, which is a part of the acquired region of interest, and it continues until the acquisition has finished. And that is all I wanted to show you. So let me thank all my colleagues from Thorsten Wohland's lab who worked with me and when I was there and worked on this topic on Imaging FCS. And so this is a picture from 2016 when I was there, and Jagadish was also there at that time. Daniel, not yet. This is Nirmala. He did a lot of work also in Imaging FCS, especially in the lipid bilayers. I also would like to thank the organizers of the I2K that I had the opportunity to share with you this workshop and show you our Imaging FCS plugin. And of course, I would like to thank you for your attention. In case you got interested in Imaging FCS, then feel free to contact us if you have any questions to it, or either to the analysis and the plugin or to the experiments. Okay, thank you for your attention, and bye.